this lab. So first you have a small write-up question. The number one, you don't have to produce any code. You just have to answer and solve the problem. Once you solve the problem and once you describe how you solve that problem, you will use what you found in number one, you will implement it in the part two, which is a programming assignment. So for this lab, we start to have write-up and programming assignment. Programming assignment is just like in April, you have some program to write in C++, and then you have to turn in those programs. Let me comment about number one. A normal stack is supporting standard operations, and those operations are push, pop, top is empty. Okay? Those operations have complexity of big of 1. They are constant time operation, and this either if you implement the stack using an array or if you implement the stack using a linked list. Both implementation can handle the operation in like big of 1, means constant time. Now, we want to add one more operation, which is a little bit strange for a stack. That operation is called find_min, and that operation is supposed to return the minimum of all the values which are currently in the stack. That operation is a non-regular operation. It's a very strange operation which is usually not supported by a stack, because a stack is only for pushing and popping values. But we assume that for some reason, in some context, we need to add that function in our stack implementation. Now, if we implement that function in a naive way, means if we look for the minimum by traversing either the array or the linked list, the complexity of the find_min function will be bigger than, where n is actually the size of the stack. Okay, so if in the stack I have n items, if I want to get the minimum by checking all the items to find the minimum, I will spend n, which is the number of items, right? So the complexity of the naive find_min I'm describing will be actually bigger than. Bigger than means linear. And actually, when we say bigger than, we should say big omega of n. Very often we mix up and we use big O all the time, although the correct function should be big omega. Big omega means minimum. Actually, in that case, it would be even a big theta, because that's the exact complexity of the find_min if we implement it in a naive way. What the problem you have to solve is you have to find a smart way to implement that special stack, and that smart way will provide all the operation push, pop, top is empty, and also find_min in constant time. You have to find a smart implementation for which the function find_min will return the minimum in big O of 1. In the number one, you don't have to write any code. You just have to describe how you can implement such a stack, which will offer those operations in big O of 1. It's only description in English, and we can even draw a small stack to explain how it works. So, for this write-up, you use, again, the sheet of paper, and you write your answer on the sheet of paper like you did for the previous write-up labs 1 and 2, and you turn in the paper. Now we move to programming assignment part 2. So now we have a programming assignment. So this assignment is like a review because you already done that last April. You're allowed to copy and paste your code if you kept your code from CSC 143. You're allowed to copy and paste it. Of course, you can reuse your code. Now that code is a little bit different because now we use slow integers. A slow integer is another kind of integer. I define it for you, and so I'm providing to you with the class slow integer. What is a slow integer? A slow integer just looks like an integer, but all the operation we do on a slow integer is very slow in compared to real integers. So the operation have been redefined for slow integer type, and they have been slowed down. So if you compare two slow integer, it takes a lot of time. Why did I do that? I did that so that you can experiment between two different implementation, and you will see very easily the difference of complexity between two different implementation. And so what you have to do is you have to implement the stack using a restack or liststack. This you can copy and paste from 143. You have to change the code a little bit because now your stacks will hold slow integers, right? So you have to change the type of the element of the items you put in the stack, which is easy, right? And now in 2.1, you have to implement the stack with find mean. You have to define the stupid find mean operation. Means the find mean operation in that implementation will use the naive linear search to find the minimum among all the item in the stack. The complexity of this function will be big theta of n. We can say big of n, but it's actually a big theta of n. Means it will be exactly linear on the size of the stack. And you can write like a small program to test your program, right? Now, after you've done that, you have to define another class, another data type, which is called Smart Stack. Smart Stack will be the implementation of what you discovered in part 1. Means that stack implementation will offer all the operation, including find mean function, in big of 1. So in that class, when we call find mean, we get the answer very quickly. Now you have a lot of supporting files. First, you find the slow integer class .h.cpp. You have to copy and put inside your code blocks, and then you have a skeleton class for array stack, list stack, and smart stack as well. You have just to fill in. And then you have a main CPP file. The main CPP is already given to you. So let me show you this one. So I just save the file first, and then I show you the file. So let me open the file for you. Wait a second. Where is my file? So that's my file. Let me open the file now with let's see with Notepad. Oh, bad move. Let's try another one. Just a second. Where is my? I'm actually not used. Okay, that's my favorite editor, Sublime Text. Let me open that editor and let me just drag the file here. Okay, so let me go back to here. Let me stop here. Here, choose that one and share. Now you see my Sublime Text editor, and you see the main function which is provided to you. That main function is actually having some code you don't have to change, and then you can just use that main to check your function. That main is doing, as you can see, is doing all kind of stuff. It is like pushing some slow integers inside the stack, and it is doing like find mean, and it's doing that for a stupid stack which is of type array stack, and then it is doing the same for a smart stack which is called smart in the code. So you don't have to change that code, but you have to write your class so that that code is working, and you will be able to compare the efficiency of the smart stack in compared to the efficiency of the stupid stack, of the array stack. And what we compare is the running time of the find min function. So that code is very easy to understand. And by the way, you can see how we can check the time, because you see the instruction, the statements, which allows us to compute the time of computation of some piece of code. You don't have to change that code, and you just have to use it. Okay, let me go back to the Firefox window. Here you see my Firefox. So all those provided files you can use, and you can copy and paste the stack implementation you have from 143. You just have to adapt it a little bit, because inside the stack we have now slow integers. That's a difference. Finally, we have a 2.2 part, which is another code you have to write. That code is fairly easy, and it's fun, because it is a kind of application, kind of a real application of the use of a stack we can have in real life. What we want to do is we want to build a robot. That robot will handle the ordering of cars in a train station. And so the goal is to automate the arranging and the sorting of train, the making up of a train. What is the problem? The problem is we have on some truck, the truck U on the right, we have cars, and the cars are numbered 0, 1, 2, 3. On the truck U, U is for unsorted. On track U, the cars are in a given order, like 1, 3, 0, 2 on the example. And what we want to rearrange the cars in a different order to make up the train. And in that example, we want to rearrange the cars so that the first is 0, then 1, 2, 3. So we want to move the cars from the right track, which is U, to the left track, which is S. And we want to change the order of the cars. And so this is one example. To do that, we have what you see. We have a special system. We can move the car from track U down to the track T, and then from track T we can move the cars either back on track U or on track S. And that's very easy to understand, because they are like trains, so there is no other way to move the cars. Okay, so actually what you are supposed to do is you are supposed to write an algorithm. So you have to write a program which will take as input U and S. So U is the current ordering of the cars on the track U. And S will describe what you want to get, the order you want to get the cars on track S. And you have to write a program which will output all the basic moves to move all the cars from track U to track S and get the ordering. On the example, this is the list of the move you have to produce to move all the cars from U to S and to get that order. So you see the car 1 should be moved from U to T, car 3 should be moved from U to T, car 0 should be moved from U to T, then car 0 should be moved from T to S. After that, we placed already the car 0. It's the first one. And then we go on. Car 3 should be moved from T back to U. Then car 1 should be moved from track T to S. After that, we placed car 0 and car 1. And we go on like that. So you are to write the program which, given the input, which is the order on track U, the order you want to get on track S, well, that program will produce will display number of moves just to rearrange the cars on the track. Now there is a question. There is a question. Don't forget to enter that question. You can answer the question by writing a comment in the file. Okay, so you can write the comment in the file, whatever, either in the main file or, well, the main file is a good choice. So you go in the main file, and at the end of the file you add a few lines of comments, and on which you answer the question. Give the best and the worst cases, running time complexity for that algorithm, and give a small example of input when those cases occur. So the best case and the worst case. Actually, to help you and to show you how easy it is, I can tell you what is a best case, because the best case is very easy to find. Best case is, for what configuration my algorithm will do the less possible work. Well, the answer is easy. If I want to get the cars in the order 0, 1, 2, 3, I need to have the cars on track U in the order 0, 1, 2, 3. Because then I do 0, I just move the car from U to T, and then from T to S, and get 0, then 1, and then 2, and then 3. In that case, the complexity is what? Well, actually, I have like one push here, and so I pop from here, I push, then I pop, and I push on the left. And so I have just like a linear algorithm which moves all the car from the right to the left. That's the best case. So up to you to find the worst case. The worst case is the configuration of the problem which will produce the biggest number of moves, right? And you have just to like give some idea of that worst case and give a small example of configuration of the cars which gives that worst case complexity. Let me come back to this now and stop the sharing. And let me ask you if you have any question.